In the next few videos, we're going to introduce some of the foundational topics for our study of trigonometry. There's a lot of information here, and we're going to move quickly, but I invite you to take your time with these videos. Pause the videos, come back and review the foundational topics as you need to. First, let's talk about angles from geometry. We can draw angles on an XY coordinate plane. The standard way to do this is to measure counterclockwise from the positive x-axis. So one side of my angle, called the initial side, begins on the x-axis. The other side is called the terminal side. So here's an example of a 45-degree angle. I could draw a 90-degree angle. 90 degrees would have initial side on the x-axis, terminal side right here. So this would be a 90-degree angle. I could draw a 180-degree angle. 180 degrees would look like this. And of course, I could draw a 360-degree angle, where the initial side and the terminal side actually coincide. 360 degrees is a full revolution. It often helps to refer to various quadrants of this XY coordinate plane. So we call this quadrant 1, quadrant 2, quadrant 3, and quadrant 4. That way, if we reference a quadrant 1, 2, 3, or 4 angle, we have a good idea of how large an angle we're talking about. Now, this is all measuring angles in degrees, as we're used to in geometry. But angles can also be measured in radians, and I'd like to introduce that idea. So imagine you have your XY coordinate plane with a shown angle, and you decide to draw a circle intersecting this angle at some point. It doesn't matter how large or small you draw your circle. But I have a diagram here that shows our angle, which we will call theta in this case. And then we drew a circle which has a given radius of the circle. And this distance is called an arc length, and we're going to use the letter S to refer to that. That's a distance around the circle, and it's the distance that is subtended by this angle or blocked off by this angle. So given this diagram, we define the radian measure of an angle as the ratio of the arc length, which is S, to the radius of the circle, which is R. So we say that theta equals S divided by R. You might see this relationship rearranged as S equals R theta. In this form, it's often called the arc length formula. But I want to think about this ratio, theta equals S over R. A couple of things that we see from this. One is that theta has no units. Theta represents an angle measure, and it has no length units because it consists of a length, S, divided by another length, R. So any units are going to divide out or cancel out. It's a number. And the second thing I want to note is that this ratio is constant no matter the size of the circle. It doesn't matter how large I draw this circle crossing my angle theta, I will always get the same ratio of S to R. The reason for that is because the circumference or distance around a circle is directly proportional to the radius. So if S increases, then R will increase as well, and this ratio will stay the same. If S decreases, R will decrease as well, and this ratio will stay the same. So this is a constant measurement, and therefore it's a good way to measure the size of our angle. Now, because the size of the circle doesn't matter, it results in a constant measurement for theta, let's use the unit circle to make our work a little bit easier. So the unit circle is a circle of radius 1 centered at the origin. It has the equation x squared plus y squared equals 1. If I am using the unit circle and I look at the ratio above, S theta equals S divided by R, then R equals 1. And so for the unit circle, we simply have the radian measure, theta, equals s, which is the arc length subtended by the angle. Let's see if we can match up some degree measures with radian measures on the unit circle. So one other thing we need to know is, how do we measure s? How do we measure the distance around a circle? Well, we know that circumference of a circle, the distance around the circle, equals 2 pi times r. And so if r equals 1, as it does on the unit circle, then we have the circumference equals 2 pi. That means if I measure s for an angle that goes all the way around, which we already know is 360 degrees, we get a measurement of 2 pi. So a 360 degree angle corresponds to 2 pi radians. I'm going to make a chart here of common degree measures and angle measures. So degrees, 360, corresponds to 2 pi. We could cut this in half. 180 degrees corresponds to pi radians. And often that is a common measurement that I will use when I'm converting between degrees and radians. 180 degrees equals pi radians. If I can remember this fact, then I can subdivide this, or I can multiply this to find other correspondence between degree measure and radian measure. So if we cut that in half again, and we look at a 90 degree angle, we will see that 90 degrees equals pi over 2. It's half of 180 degrees, so the radian measure is half of pi. If we cut it in half again, we get 45 degrees, and that will equal pi over 4. 270 degrees is at the third quadrant right here. 270 degrees is pi over 2 plus pi over 2 plus pi over 2. So that equals 3 pi over 2. And finally, two other important angles that we often work with, 30 degrees and 60 degrees. We'll add the radian measures for those in a minute. So if I'm moving back and forth between radian and degree measure, I like to remember this fact that 180 degrees equals pi radians. So to convert degrees to radians, you can multiply by this factor of pi over 180. Those are equivalent to each other. To convert radians to degrees, I can multiply by 180 over pi. So for example, if I want to find 60 degrees in radians, I can take 60 degrees times pi over 180 degrees. This is 60 pi over 180. Degree measures will cancel out here, or divide out. So that's the same as 6 pi over 18, which is the same as pi over 3. So 60 degrees in radians must be pi over 3. We can add that to our chart. 30 degrees will be half of that, so that will be pi over 6. So we have a completed chart here of degree and radian measure. Let's do one more calculation. Find 3 pi over 4 in degrees. 3 pi over 4 times the factor of 180 over pi. Notice these values of pi will divide out as well. And we'll get 3 times 180 divided by 4. It may help first to do some simplifying. I could divide these by 2 and divide by 2 again. I end up with 3 times 45, which is 135 degrees. 3 pi over 4 radians is the same as 135 degrees.